5,000 years ago, under the endless desert sky of ancient Mesopotamia, priests gathered on ziggurat rooftops as darkness fell. They watched the same stars you see tonight, but with a different understanding. These weren't distant suns scattered across space. To them, these were holes in the celestial sphere, divine lights fixed to a rotating dome that enclosed the world. They carved their observations into clay tablets, marking the movements of planets, tracking the seasons, building the foundation of astronomy. They didn't know it, but they were beginning humanity's greatest conversation with the cosmos. For thousands of years, that conversation was quiet. The stars moved in their predictable patterns. The sun rose and set. The moon cycled through its phases. Everything seemed to revolve around Earth, the obvious center of creation. It was comfortable, comprehensible, and utterly wrong. Then came 1610. In Padua, Italy, a mathematics professor named Galileo Galilei heard rumors of a Dutch invention, a tube with lenses that made distant objects appear closer. Within weeks, he built his own version, grinding the lenses himself. But Galileo didn't just want to see distant ships. He pointed his telescope at the night sky. Picture this moment. It's January 7th, 1610. Galileo steadies his hand against the cold window frame in his study. Through the crude lens, barely more powerful than modern binoculars, Jupiter appears not as a point of light, but as a disk. And beside it, 3 tiny stars in a perfect line. The next night, they've moved. The night after that, a 4th appears. Over the following weeks, he watches these points of light dance around Jupiter in a cosmic ballet that could mean only one thing. These weren't stars at all. They were moons, orbiting Jupiter. Here's what's really happening in that moment. Galileo's trembling hands are holding evidence that destroys 1,500 years of cosmic certainty. If moons orbit Jupiter, then not everything circles Earth. The Earth isn't the center of the universe. The Copernican model, that radical idea that we orbit the sun, isn't just mathematical convenience. It's reality. The Church didn't take this well. But the truth was already escaping into the world, carried by Galileo's published observations. You couldn't put this discovery back in the bottle. The universe was bigger and stranger than anyone had imagined, except for one man who imagined it was infinitely bigger and infinitely stranger. Giordano Bruno was a Dominican friar who couldn't stop thinking dangerous thoughts. While Galileo carefully measured Jupiter's moons, Bruno made a conceptual leap that was breathtaking in its audacity. He proposed that the stars weren't holes in a celestial sphere or distant ornaments. They were other suns, and around those suns might orbit other worlds, and on those worlds might live other beings, looking up at their own skies, wondering if they were alone. Infinite space, infinite worlds, infinite possibilities. The Catholic Church found this unacceptable. On February 17th, 1600, in Rome's Campo de' Fiori, they burned him alive. But here's the extraordinary thing. As the flames rose, as medieval certainty tried to incinerate radical thought, Bruno was right. Every star you see is indeed another sun. Most of them host planets. The universe is more vast than even Bruno imagined. The weight of infinity began crushing the comfortable medieval cosmos. The conversation with the stars was becoming less comfortable and far more honest. Fast forward to 1786. In Bath, England, a woman named Caroline Herschel is helping her brother William with his massive telescope. Caroline wasn't supposed to be an astronomer. Women weren't astronomers. But night after night, she worked beside her brother, taking notes, performing calculations, and eventually making her own observations. She discovered 8 comets. She became the first woman to receive a salary for scientific work. But more importantly, she represented something profound. The cosmos didn't care about human social conventions. The universe revealed itself to anyone willing to look carefully enough. The Herschels weren't just finding comets, they were mapping the architecture of the heavens. William discovered that our sun moves through space, that we're traveling toward the constellation Hercules. The stars weren't fixed, nothing was fixed, everything was in motion. By the late 19th century, astronomers faced a maddening problem. They could see countless galaxies, fuzzy spiral shapes scattered across the sky. But were these objects inside our Milky Way galaxy, or were they separate galaxies entirely? The question sounds academic, but it determined the scale of everything. Was the universe one galaxy or millions? Was it thousands of light years across or billions? The key to answering this question came from an unlikely source. A young woman working as a computer at Harvard College Observatory. Her name was Henrietta Swan Leavitt. In the early 1900s, computers were people, usually women, hired to perform tedious mathematical calculations and examine astronomical photographs. It was considered menial work beneath male astronomers. But Leavitt brought something extraordinary to these routine observations. She noticed a pattern. She was studying Cepheid variable stars, stars that pulse, brightening and dimming in regular cycles. Some pulsed every few days, others every few weeks. Leavitt noticed that the longer the pulse period, the brighter the star's maximum luminosity. This relationship was precise, mathematical, and revolutionary. Here's why this matters. If you know a star's true brightness, and you measure how bright it appears from Earth, you can calculate its distance. It's like seeing a 100-watt light bulb. If it looks dim, it's far away. If it looks bright, it's close. Leavitt had discovered a cosmic measuring stick. Cepheid variables became standard candles, reliable reference points for measuring the universe. In 1923, Edwin Hubble, yes, the Hubble Space Telescope is named after him, used Leavitt's discovery to measure the distance to the Andromeda Nebula. His result was shocking, 2.5 million light-years away. This meant Andromeda was far beyond the boundaries of the Milky Way. It was another galaxy entirely. In fact, it was larger than our own galaxy. In that moment, the universe exploded in size again. There weren't thousands of stars, but hundreds of billions. And there weren't just stars in one galaxy, but hundreds of billions of galaxies, each containing hundreds of billions of stars. The numbers became incomprehensible, the scale became nauseating, and the most disturbing discovery was yet to come. Hubble kept measuring. He found Cepheids in galaxy after galaxy, calculating their distances. Then he did something clever. He measured their redshift, how much their light had shifted toward the red end of the spectrum as they moved away from us. What he discovered in 1929 changed everything. The farther away a galaxy was, the faster it was moving away from us. This wasn't just a few nearby galaxies drifting apart. This was every galaxy in every direction, racing away at speeds proportional to their distance. The only explanation: space itself was expanding. The universe wasn't static, it was growing. Run this expansion backward, and you reach an inescapable conclusion. Everything was once in the same place. The universe had a beginning. For decades, this remained controversial. Many scientists, including Einstein initially, found the idea of a cosmic beginning philosophically troubling. Surely the universe was eternal, unchanging in its grand structure, even if individual stars were born and died. The idea of creation from nothing felt too much like theology sneaking into physics. Then came 1964. Two radio astronomers, Arno Penzias and Robert Wilson, were trying to eliminate noise from a sensitive antenna at Bell Labs in New Jersey. No matter what they did, cleaning out pigeon droppings, reorienting the antenna, checking every connection, they couldn't get rid of a persistent hiss. It came from every direction, constant, unchanging, and deeply annoying. They were about to publish a paper about mysterious interference when they learned about theoretical work being done at nearby Princeton University. Physicists there had predicted that if the universe began in a hot, dense state and expanded, the afterglow of that initial heat should still be detectable today. It would have cooled over billions of years, but it should still be there, a faint microwave signal coming uniformly from every direction. The temperature of this cosmic microwave background radiation, it should be about 3 degrees above absolute zero. Penzias and Wilson measured their mysterious noise. 2.7 degrees Kelvin above absolute zero. Here's what's really happening. That annoying static wasn't interference. It was the echo of creation itself. When Penzias and Wilson listened to their antenna, they were hearing the universe as it was 380,000 years after the Big Bang, when space finally cooled enough for light to travel freely. That light has been traveling through expanding space for 13.8 billion years, stretched from visible light into microwaves by the universe's expansion. You are bathed in the afterglow of the Big Bang right now. It's everywhere, uniform to within 1 part in 100,000, a testament to the incredible smoothness of the early universe and the violent beginning that preceded it. This discovery earned Penzias and Wilson the Nobel Prize in 1978. More importantly, it settled the debate. The universe had a beginning. Space itself came from something so small, so dense, and so hot that our normal understanding of physics breaks down. From Mesopotamian priests carving observations into clay, to Galileo's trembling hands revealing Jupiter's moons, to Bruno's fatal vision of infinite worlds, to Leavitt's patient work revealing cosmic distances, to Hubble's shocking discovery of expansion, to the accidental detection of creation's echo, each step expanded our understanding and humbled our place in the cosmos. The conversation that began 5,000 years ago under the Mesopotamian sky had led us to this. We live in an expanding universe, born from an unimaginably dense beginning, growing and cooling for nearly 14 billion years. We exist on a small planet orbiting an ordinary star in an ordinary galaxy, one of hundreds of billions of galaxies stretching across billions of light years. But understanding where we are is just the beginning. The next question is deeper and more difficult. How did we get here? What happened in those first moments after the universe began? What forces shaped the cosmos into the intricate architecture we observe today? The answer begins in the first trillionth of a trillionth of a trillionth of a second after time began. It's a story of forces splitting apart, particles forming from pure energy, and space itself stretching faster than light, all in less time than it takes a photon to cross an atomic nucleus. The conversation with the cosmos was about to get much stranger. 13.8 billion years ago there was nothing, no space, no time, no matter, no energy. Then, in less time than it takes light to cross the width of a proton, everything exploded into existence. This wasn't an explosion in space. This was an explosion of space itself. Imagine trying to visualize nothing, not empty space, because even emptiness is something. True, nothing. No dimensions, no before, no elsewhere. Then suddenly, in a fraction of a second so small that writing out the decimal would require more zeros than you could fit on this page, the universe expanded from smaller than a quantum fluctuation to larger than a galaxy. This is inflation theory, and it sounds absurd. But here's what's remarkable. It explains why the universe looks the way it does. Remember that cosmic microwave background radiation discovered by Penzias and Wilson? It's uniform to an extraordinary degree. The temperature is the same in every direction to within 1 part in 100,000. For different regions of space to have the same temperature, they must have been in contact, able to exchange energy and equalize their heat. But if the universe expanded at the speed we observe today, regions on opposite sides of the sky were never in contact. They're too far apart. They never could have equalized their temperature, unless, in the very beginning, everything was in contact. Unless there was a moment when the entire observable universe was smaller than an atom, when every region could interact and reach equilibrium, then inflation stretched space so fast that these regions flew apart, carrying their identical temperatures with them, preserving that original uniformity. In the first trillionth of a trillionth of a trillionth of a second, 10 to the negative 36 seconds, space expanded by a factor of at least 10 to the 26. That's a 1 followed by 26 zeros. A region the size of a proton became larger than our entire observable universe today. Space stretched faster than light, which sounds impossible until you remember that nothing prevents space itself from expanding faster than light. The cosmic speed limit applies to objects moving through space, not to space itself. During this inflation, the universe was unimaginably hot, 10 to the 27 degrees Kelvin. At this temperature, the four fundamental forces that govern everything were unified into a single force: gravity, electromagnetism, the strong nuclear force, and the weak nuclear force were one thing. Then the cosmic egg cracked. As the universe expanded and cooled, these forces split apart in a process called symmetry breaking. Imagine water freezing into ice. Liquid water looks the same in every direction. It has perfect symmetry, but when ice forms, it creates crystals with specific orientations. The symmetry breaks. Something similar happened to the fundamental forces. First, gravity separated. It became its own force, the weakest of the four, but with infinite range, able to reach across the universe and pull galaxies toward each other. Gravity curves space itself, creating the architecture upon which everything else would be built. Then the strong nuclear force split off. This is the force that holds atomic nuclei together, binding protons and neutrons despite the electromagnetic repulsion between positively charged protons. It's the strongest force in nature, but it only works at distances smaller than an atomic nucleus. Step outside that range, and its power vanishes. The weak nuclear force separated next. It's responsible for radioactive decay, for the transformation of one type of particle into another. It's crucial for the sun's fusion reactions, for the formation of heavy elements, for the very possibility of chemistry and life. Finally, electromagnetism, the force between charged particles, the power behind lightning and magnetism and light itself. This is the force you experience most directly in daily life. When you touch a table, you're not actually touching it. The electrons in your hand and the electrons in the table repel each other electromagnetically. You live your entire life without ever truly touching anything. By the time the universe was 10 to the negative 32 seconds old, these four forces had separated into their distinct identities. The rules of physics as we know them were in place, but there was still no matter, only energy, pure and undifferentiated. As space continued expanding and cooling, that energy began condensing into particles. First came quarks and gluons, the fundamental building blocks that would eventually form protons and neutrons. They existed in a searingly hot soup called quark-gluon plasma, too energetic for these particles to bind together into anything more complex. 1 second after the Big Bang, the universe had cooled to 10 billion degrees Kelvin. That's cooler than the core of a massive star. In this slightly less extreme environment, quarks could finally bind together. 3 quarks joined to form a proton. 3 different quarks formed a neutron. The basic building blocks of atomic nuclei had arrived. But here's something strange. For every billion particles of matter, there was 1 billion particles of antimatter. When matter and antimatter meet, they annihilate, converting back into pure energy. By all rights, everything should have destroyed itself, leaving a universe of pure light with no matter at all. Yet here we are. Something created a tiny asymmetry, 1 extra matter particle for every billion matter-antimatter pairs. Those billion pairs annihilated each other, flooding the young universe with gamma rays. That one extra particle of matter survived. Everything you see, every star, every planet, every atom in your body comes from that tiny imbalance. We exist because of a 1 in a billion asymmetry that nobody fully understands. 3 minutes after the Big Bang, the universe had cooled to 1 billion degrees. This is cool enough for nuclear fusion to begin. Protons and neutrons started sticking together, forming the first atomic nuclei. 2 protons and 2 neutrons joined to create helium-4, the second lightest element. A few other light nuclei formed deuterium, helium-3, traces of lithium. This process, called Big Bang nucleosynthesis, lasted about 17 minutes. Then, the universe cooled below the temperature needed for fusion. The nuclear forges shut down. When it was over, the universe consisted of roughly 75% hydrogen and 25% helium, by mass, with tiny traces of lithium. Those ratios are crucial. Measure the hydrogen and helium in the oldest stars today, and you find exactly these proportions. It's one of the most powerful confirmations of the Big Bang theory. The universe remembers its first 17 minutes, but atoms still couldn't form. The universe was too hot. Any electron that tried to orbit a nucleus would be immediately kicked away by energetic photons. Space was opaque, a blinding fog of light and plasma, where photons could only travel a tiny distance before colliding with a free electron. 380,000 years passed. The universe expanded and cooled. Finally, the temperature dropped to about 3,000 degrees Kelvin, hot enough to glow like the heating element in a toaster, but cool enough for electrons to bind to nuclei without being immediately knocked away. This moment is called recombination, though that's a misnomer since electrons and nuclei had never been combined before. Suddenly, atoms could hold together. Hydrogen atoms formed 1 proton, 1 electron. Helium atoms formed 2 protons, 2 neutrons, 2 electrons. With free electrons now bound into atoms, photons could finally travel freely through space. The universe became transparent. Light was released. That light is the cosmic microwave background radiation that Penzias and Wilson detected, stretched from visible light into microwaves by nearly 14 billion years of cosmic expansion. When you look at images of the cosmic microwave background, you're seeing the baby picture of the universe at 380,000 years old, the oldest light we can possibly detect. But the universe at this point was remarkably boring. Just hydrogen and helium gas, spread almost uniformly through space, cooling and expanding into a long, dark night. No stars, no planets, no complex chemistry. Nothing interesting could happen with just hydrogen and helium, except for one thing: gravity. Remember, the cosmic microwave background is uniform to 1 part in 100,000. That means it's not perfectly uniform. There are tiny fluctuations, regions slightly denser than average, regions slightly less dense. These variations are incredibly small, but gravity amplifies them. A region that's slightly denser has slightly more mass, which means slightly stronger gravity, which pulls in more matter from surrounding regions, which increases the density further, which strengthens gravity more. It's a feedback loop. Dense regions become denser, sparse regions become emptier. Over millions of years, these tiny fluctuations grew. The universe began developing structure. Hydrogen and helium flowed toward the densest regions like water flowing downhill, accumulating into vast clouds hundreds of light years across. 200 million years after the Big Bang, these clouds reached a critical threshold. The pressure and temperature at their cores rose high enough to ignite fusion. Hydrogen atoms slammed together with enough force to overcome their electromagnetic repulsion. 4 hydrogen nuclei fused into 1 helium nucleus, converting a tiny amount of mass into energy according to Einstein's famous equation. That energy emerged as light and heat. The first stars were born. These weren't stars like our sun. They were monsters 100 times more massive, thousands of times brighter, burning blue-white at surface temperatures of 100,000 degrees. They consumed their hydrogen fuel at prodigious rates, fusing heavier and heavier elements in their cores. Carbon formed from helium, oxygen formed from carbon, silicon, sulfur, iron. The periodic table assembled itself in the hearts of these stellar giants. But massive stars live fast and die young. Within just a few million years, a cosmic eye blink, these first stars exhausted their fuel. When a massive star runs out of nuclear fuel, nothing can prevent its core from collapsing under its own gravity. The core implodes, then rebounds in one of the universe's most violent events, a supernova explosion. In seconds, a single star releases more energy than an entire galaxy. The explosion is so violent that it forges elements heavier than iron, gold, platinum, uranium. It blasts these newly created elements into space at a significant fraction of the speed of light. The enriched gas spreads outward, mixing with the pristine hydrogen and helium that still makes up most of the universe's matter. Here's what's really happening. Every atom in your body heavier than hydrogen was created inside a star. The carbon in your cells, the calcium in your bones, the iron in your blood, all of it was forged in stellar furnaces billions of years ago, then scattered into space when those stars exploded. We are made of star stuff. Not poetically, literally. As the first generation of stars died, they enriched the universe with heavy elements. The next generation of stars that formed included these elements in their composition. These stars could form planets, because you can't make a rocky planet from just hydrogen and helium. You need silicon, oxygen, iron, magnesium, the heavy elements that only exist because previous generations of stars created them. But stars weren't forming randomly throughout space. Gravity was sculpting the universe on the largest scales imaginable. Dark matter, we'll explore this mysterious substance in detail later, makes up 85% of all matter in the universe. It doesn't emit light, doesn't absorb light, doesn't interact with electromagnetic radiation at all. We only detect it through its gravitational effects. And in those first few 100 million years, dark matter's gravity was the dominant force shaping cosmic structure. Dark matter collapsed into vast filaments and sheets, creating an invisible scaffolding stretching across hundreds of millions of light years. Normal matter, the hydrogen and helium gas that makes up stars and galaxies, followed the gravitational contours defined by this dark matter architecture. The result is the cosmic web, the largest structure in the universe. If you could see the distribution of galaxies across billions of light years, you'd observe something that looks uncannily like neural pathways in a brain or the structure of a spider's web. Long filaments where galaxies cluster densely, connected by thinner bridges surrounding vast voids. These voids are genuinely empty, not in the sense of being vacuum, but in the sense of containing almost no galaxies. If you travelled through the centre of a supervoid, you could look in any direction and see no galaxies for 300 million light years, just darkness and the faint glow of the cosmic microwave background. It would be profoundly lonely, and it would take hundreds of millions of years travelling at the speed of light to escape. Meanwhile, at the intersections of cosmic web filaments, where the dark matter density is highest, matter pours inward from all directions. These become the sites of galaxy clusters, collections of hundreds or thousands of galaxies bound together by gravity, containing quadrillions of stars. Our own Milky Way galaxy formed about 13 billion years ago, just 800 million years after the Big Bang. It started small, a dwarf galaxy perhaps, containing tens of millions of stars. Over billions of years, it grew by merging with other galaxies, cannibalizing its neighbors, accumulating mass and angular momentum until it became the spiral galaxy we see today, containing between 200 billion and 400 billion stars. At its center lurks something dark and powerful, a supermassive black hole containing 4 million times the Sun's mass. Nearly every large galaxy has one. How they formed so early in the universe's history remains mysterious, but their gravity helps hold their host galaxies together, their immense mass anchoring the stellar orbits. Around some of these stars, planets formed. Dust and gas left over from stellar formation coalesced into orbiting bodies. Rocky planets like Earth formed in the inner regions where it was hot. Gas giants like Jupiter formed in the outer regions where ice and gas could accumulate. Some of these planets ended up in the habitable zone, not too hot, not too cold, where liquid water could exist on their surface. On at least one of these planets, something remarkable happened. But that story belongs later in our journey. For now, understand this. From a universe that began as pure energy in a space smaller than an atom, gravity and the four fundamental forces sculpted everything we see. Particles formed from energy, atoms formed from particles, stars formed from atoms, heavy elements formed in stars, galaxies formed from clouds of gas and dark matter. Structure emerged from near uniformity through the patient, persistent pull of gravity, amplifying tiny initial fluctuations. The architecture of everything from the largest cosmic web filaments to the smallest atoms emerged from simple rules playing out across billions of years and trillions of light years. The universe started simple and grew complex. It started smooth and grew structured. It started hot and grew cool. And through it all, threaded invisibly through every galaxy and cluster, woven into the very fabric of the cosmic web, is something we still don't understand. Something that outweighs everything we can see by 5 to 1. Something that shapes the universe's architecture while remaining completely invisible. Dark matter. And its even stranger cousin, dark energy. Their story is next, and it's a tale of invisible hands pulling cosmic strings, of the universe accelerating against all expectation, and of our growing realization that we understand less than 5% of what exists. The visible universe, all the stars, all the galaxies, all the light we can detect is just the foam on an ocean we're only beginning to comprehend. In 1933, a Swiss astronomer named Fritz Zwicky was doing something that sounds simple, weighing a galaxy cluster. The Coma cluster contains over 1,000 galaxies, and Zwicky wanted to know how much mass held them together. He measured how fast the galaxies were moving. They were orbiting the cluster's center at extraordinary speeds, hundreds of kilometers per second. Here's the thing about orbits. The faster something moves, the more gravity it needs to keep it from flying apart. It's like swinging a ball on a string. The faster you spin it, the stronger you have to grip the string. If the string isn't strong enough, the ball flies away. Zwicky calculated how much mass the cluster needed to keep those fast-moving galaxies from escaping into intergalactic space. Then he added up all the visible mass, all the stars in all the galaxies, all the gas clouds, everything that emitted light. The numbers didn't match, not even close. The visible matter could only account for about 1/6 of the mass needed to hold the cluster together. The galaxies were moving so fast that they should have torn the cluster apart billions of years ago. Yet there they were, still bound together, still orbiting. Zwicky proposed something radical. There must be dunkel, materie, dark matter, invisible mass, that outweighed everything we could see by a factor of 5 to 1. The visible universe, he suggested, was just a tiny fraction of what existed. Most of the cosmos was hidden in darkness. Nobody believed him. It was too strange, too unsettling. Surely there was a simpler explanation. Maybe he'd made an error in his calculations. Maybe there were measurement problems. The idea sat on the shelf for decades, a curious anomaly that most astronomers chose to ignore. Then came Vera Rubin. In the 1970s, Rubin was measuring how fast stars orbit within galaxies. She focused on spiral galaxies, examining stars at different distances from the galactic center. Newton's laws made a clear prediction. Stars farther from the center should orbit more slowly, just as planets farther from the Sun take longer to complete their orbits. Mercury races around the Sun in 88 days. Neptune takes 164 years. The farther out you go, the slower the orbital speed. But that's not what Rubin found. Stars at the edge of galaxies were moving just as fast as stars near the center. In some cases, they were moving even faster. According to visible matter alone, these outer stars should be moving so fast that they'd fly off into intergalactic space like a ball slipping from a loosened string. Yet they stayed in orbit, held by gravity that seemed to come from nowhere. Rubin measured galaxy after galaxy. The pattern held. Every spiral galaxy she examined showed the same impossible rotation curve. The visible matter stars and gas clouds couldn't possibly provide enough gravity. There had to be something else, something invisible, something that extended far beyond the visible disk of each galaxy, like an enormous invisible halo. Dark matter had announced itself again, this time with overwhelming evidence. Here's what's really happening. When you look at a galaxy like the Milky Way, the stars and glowing gas clouds you see are just the visible tip of a vast invisible structure. Surrounding and permeating every galaxy is a halo of dark matter, perhaps 10 times larger than the visible galaxy itself. Most of a galaxy's mass isn't in its stars. It's in this invisible halo that we detect only through its gravitational pull. But what is dark matter? That's the maddening question that still haunts physicists 50 years after Rubin's discovery. It's not ordinary matter that happens to be dark. We've ruled that out. It's not black holes or brown dwarfs or dark planets. Those are all made of normal atoms, protons, neutrons, electrons, and we can calculate the maximum amount of normal matter that could have formed in the Big Bang. It's not enough. Not nearly enough. Dark matter must be something else entirely. Something that doesn't interact with light at all, doesn't emit it, doesn't absorb it, doesn't reflect it. It passes through electromagnetic radiation as if the photons weren't there. To dark matter, the entire electromagnetic spectrum might as well not exist. Yet dark matter does interact gravitationally. It has mass, and mass curves space-time according to Einstein's general relativity. This curvature affects everything: the motion of stars, the rotation of galaxies, the trajectories of light itself. This last effect gives us one of our most powerful tools for detecting dark matter: gravitational lensing. Imagine looking at a distant galaxy through a massive galaxy cluster. The cluster's gravity, dominated by its dark matter, bends space-time like a bowling ball placed on a trampoline. Light from the distant galaxy follows the curved space-time, bending around the cluster like water flowing around a rock. From our perspective, the distant galaxy appears distorted, stretched into arcs and rings around the cluster. By measuring this distortion, astronomers can map the dark matter distribution in the cluster. And when they do this for colliding galaxy clusters, they see something remarkable. The dark matter and the visible matter separate. The bullet cluster provides the most dramatic example. Two galaxy clusters collided at speeds of millions of kilometers per hour. The normal matter, the hot gas that fills the space between galaxies, crashed together, colliding and heating up to hundreds of millions of degrees. This hot gas emits X-rays, so we can see it, but the dark matter passed right through. It doesn't collide with itself. It doesn't interact with normal matter except through gravity, while the visible matter slowed down and piled up at the collision site. The dark matter halos sailed through each other like ghosts passing through walls, continuing onward with barely any interaction. Gravitational lensing reveals the dark matter's location, and it's not where the visible matter is. The two have separated. This rules out alternative theories that try to explain galaxy rotation without invoking dark matter. There's genuinely something there, something with mass, something invisible that outweighs everything we can see. Physicists have proposed dozens of candidate particles for dark matter. WIMPs, weakly interacting massive particles, axions, sterile neutrinos, particles that exist in theories beyond the standard model of particle physics. Experiments deep underground, shielded from cosmic rays, wait in the darkness for a dark matter particle to collide with their detectors. So far, nothing. The dark matter particles, if that's what they are, remain frustratingly elusive. We know dark matter makes up 85% of all matter in the universe. We know it shaped the cosmic web, providing the gravitational scaffolding along which galaxies formed. We know it holds galaxies and galaxy clusters together, but we don't know what it is. It's one of the most profound mysteries in modern physics. And then there's something even stranger. In 1998, two teams of astronomers were racing to measure how fast the universe's expansion was slowing down. It seemed obvious that expansion should be slowing. Every galaxy pulls on every other galaxy through gravity. This should decelerate the expansion, like friction, gradually slowing a spinning top. The question was, how fast is the deceleration? Is there enough matter in the universe for gravity to eventually stop the expansion and pull everything back together in a big crunch? Or is there too little matter, meaning the universe will expand forever, but at an ever-slowing rate? Both teams use the same technique, measuring type Ia, supernovae in distant galaxies. These supernovae are remarkably consistent in their maximum brightness, making them excellent standard candles for measuring cosmic distances. By comparing how bright these supernovae appear with how bright they should be, astronomers can calculate their distance. By measuring their redshift, they can determine how fast space was expanding when that light was emitted. Measure enough distant supernovae, and you can map the expansion history of the universe. You can determine whether the expansion is slowing down, and by how much. Both teams analyzed their data. Both teams checked and rechecked their calculations. Both teams reached the same impossible conclusion. The expansion wasn't slowing down, it was speeding up. Imagine driving a car, taking your foot off the accelerator, and having the car speed up instead of slowing down. That's what the universe is doing. Something is pushing galaxies apart, and that push is getting stronger over time. This discovery earned the team leaders the Nobel Prize in 2011. It also plunged cosmology into crisis. What could possibly cause the universe to accelerate? The answer, or at least the name for the answer, is dark energy. Dark energy is even more mysterious than dark matter. Dark matter at least behaves like matter. It clumps together, forms structures, and creates gravitational wells. Dark energy does the opposite. It's smoothly distributed throughout all of space, and it pushes outward rather than pulling inward. It has negative pressure, which sounds like a contradiction until you dig into the mathematics of general relativity. In Einstein's equations, both energy and pressure curve space-time. Positive pressure, like the pressure inside a star, creates a gravitational attraction, but negative pressure creates gravitational repulsion. It pushes things apart rather than pulling them together. Here's the disturbing part. Dark energy makes up about 70% of everything in the universe. Dark matter makes up about 25%. Normal matter, everything we can see, every star, every galaxy, every atom in your body, makes up less than 5%. We live in a universe where 95% of its content is completely invisible to us and fundamentally mysterious. We're like someone trying to understand an elephant while only being able to perceive its tail. The simplest explanation for dark energy is something called the cosmological constant. Einstein actually introduced this concept in 1917, before Hubble discovered that the universe was expanding. Einstein's equations predicted that a static universe should collapse under its own gravity, but Einstein believed the universe was eternal and unchanging, so he added a constant to his equations, a term that represented a fixed energy density of empty space itself. When Hubble discovered cosmic expansion, Einstein called the cosmological constant his biggest blunder and removed it from his equations. But now it's back, resurrected to explain dark energy. If the cosmological constant is real, then every cubic meter of empty space contains energy, not much the equivalent energy of roughly 1 hydrogen atom per cubic meter, but space is vast, and all this energy adds up. More importantly, as space expands and creates more volume, it creates more dark energy. The total amount of dark energy in the universe increases over time. This creates a feedback loop. Dark energy pushes space apart. The expansion creates more space. More space contains more dark energy. More dark energy accelerates the expansion faster. And so on, forever, accelerating exponentially. But here's where physics encounters one of its most embarrassing problems. Quantum field theory, our best description of particles and forces, predicts that empty space should indeed have energy. Quantum fluctuations, the temporary appearance and disappearance of particle-antiparticle pairs, should fill the vacuum with energy. This prediction is rock solid. The theory works. It's been tested to incredible precision. But when physicists calculate how much vacuum energy quantum field theory predicts, the number they get is absurdly large. Then they measure how much dark energy actually exists. The measured value is smaller than the prediction by a factor of 10 to the 120. That's 1 followed by 120 zeros. This is not a small discrepancy. This is the worst prediction in the history of physics. Imagine trying to predict someone's weight and being off by not just a few pounds, but by the mass of the entire observable universe, multiplied by itself a trillion times. This is the cosmological constant problem, and nobody knows how to solve it. Either quantum field theory is profoundly wrong about vacuum energy, or there's some mechanism that cancels out almost all of it, leaving just the tiny amount we observe as dark energy. But what mechanism? No one knows. Some physicists propose that dark energy isn't constant, but changes over time, a concept called quintessence. Others suggest modifications to general relativity itself at the largest scales. Still others think dark energy might be an illusion arising from how we average the universe's structure, though most physicists find this unconvincing given the supernova data. What we do know is that dark energy's effects are real and measurable. Distant galaxy clusters are already moving away from us so fast that their light will never reach us. Space between us and them is expanding faster than light can cross it. These clusters have crossed our cosmic horizon and are gone forever, even though they still exist. Billions of years in the future, as dark energy continues accelerating the expansion, even nearby galaxy clusters will recede beyond the horizon. Eventually, distant galaxies will fade from view, their light stretched to infinitely long wavelengths. The universe will appear to future astronomers as it appeared to ancient ones, a single island of stars surrounded by darkness, with no evidence that anything exists beyond. In about 150 billion years, if dark energy remains constant, only our local group of galaxies, the Milky Way, Andromeda, and a few dozen smaller galaxies bound tightly together will remain visible. Everything else will have receded beyond the horizon, unreachable not because of distance but because of the accelerating expansion of space itself. Here's what's really happening. We live in a special time, a time when the universe is old enough to have formed complex structures like galaxies and stars and planets, but young enough that we can still see most of it. Billions of years from now, intelligent beings in our galaxy would have no way to discover the Big Bang, no way to see the cosmic web, no way to measure the universe's expansion. The evidence would have literally moved beyond reach. We're fortunate to exist in a cosmic moment when the universe is still revealing its secrets. But this raises a deeper question. Why does dark energy have exactly the value it does? If it were slightly stronger, galaxies would never have formed. Space would have expanded too quickly for gravity to pull matter into structures. If it were slightly weaker, or if it didn't exist at all, the universe's evolution would be dramatically different. The same is true for dark matter. If there were no dark matter, galaxies would fly apart. Stars would drift off into the void. If there were too much dark matter, structures would collapse into black holes before stars could form. The universe appears fine-tuned for complexity, for structure, for the possibility of life. Change any of these fundamental parameters by even a small amount, and the universe becomes sterile, empty, incapable of producing anything interesting. Is this fine-tuning just extraordinary luck? Or does it point to something deeper, perhaps a multiverse where every possible value occurs, and we necessarily exist in one where the values permit our existence? These questions push us toward the frontier of cosmology, toward ideas that border on philosophy. But before we dive into multiverses and cosmic company, we need to understand what else exists in this universe we're beginning to map. We need to ask one of humanity's oldest questions. Are we alone? The search for that answer has become one of the most exciting pursuits in modern astronomy, taking us from golden records flying through interstellar space to exoplanets orbiting distant stars, to tantalizing hints of chemistry on Venus that might be, life floating in acid clouds. That search begins now. In 1961, a radio astronomer named Frank Drake gathered a small group of scientists in Green Bank, West Virginia. They faced a question that had haunted humanity since the first person looked up at the stars. Are we alone? Drake approached this ancient question with the tools of a scientist. He wrote an equation on the blackboard, not a formula that could be solved with precision, but a framework for thinking about the probability of finding intelligent life in our galaxy. Start with the rate at which new stars form in the Milky Way. Multiply by the fraction of stars that have planets. Multiply by the number of planets per star that could support life. Multiply by the fraction where life actually develops. Multiply by the fraction where life becomes intelligent. Multiply by the fraction that develops technology capable of interstellar communication. Finally, multiply by how long such civilizations survive and broadcast signals into space. The Drake equation doesn't give you an answer. It gives you a way to organize your uncertainty. Every term is either poorly known or completely unknown. But even conservative estimates suggested something remarkable. Our galaxy alone might harbor thousands of Cartes, technological civilizations, maybe even tens of thousands. If that's true, where are they? This question has become known as the Fermi paradox, named after physicist Enrico Fermi, who supposedly asked during a lunch conversation, "Where is everybody?" The universe is 13.8 billion years old. Our galaxy is 13 billion years old. Earth is only 4.5 billion years old. There's been plenty of time for intelligent life to arise, develop technology, and spread across the galaxy. Even without faster-than-light travel, a civilization could colonize the entire Milky Way in just a few million years using slow generation ships. That's a cosmic eye blink. If intelligent life is common, someone should have done this already. The galaxy should be teeming with evidence of technological civilizations, radio signals, megastructures, signs of stellar engineering. Yet when we listen, we hear only silence. This silence is profound and disturbing. 50 years of searching with increasingly sensitive instruments has yielded nothing convincing, no deliberate signals, no obvious signs of artificial structures, no hello broadcast from the stars. In 1977, NASA decided to send a message anyway. 2 spacecraft, Voyager 1 and Voyager 2, launched on trajectories that would take them past Jupiter, Saturn, and out into interstellar space. Each carried a golden record, a 12-inch gold-plated copper disc containing sounds and images from Earth. The contents read like a love letter to the cosmos. Greetings in 55 languages, music from Bach to Chuck Berry, sounds of rain and thunder, and whales singing, images of human faces, animals, cities, and DNA structure. The record includes a diagram showing Earth's location relative to 14 pulsars, cosmic lighthouses, that any advanced civilization could use to find us. The Voyagers have now traveled beyond the edge of our solar system into interstellar space. They're over 20 billion kilometers from Earth, carrying humanity's greatest hits into a void where the nearest star is still 40,000 years away at their current speed. Here's the sobering reality. The golden records will likely never be found. Space is incomprehensibly vast and mostly empty. The chances of an alien civilization intercepting a 12-inch disk drifting through the darkness are essentially zero. The Voyager missions weren't really about communicating with aliens. They were about humans expressing hope that we're not alone, that somewhere out there, someone might be listening. But while we've been sending optimistic messages, we've also been searching. And that search has revealed something extraordinary. Planets are everywhere. In 1995, astronomers detected the first planet orbiting a sun-like star. It was a strange world, a gas giant larger than Jupiter, orbiting closer to its star than Mercury orbits our Sun. A hot Jupiter, as these worlds came to be called, with surface temperatures hot enough to vaporize metal. This was just the beginning. The Kepler Space Telescope, launched in 2009, stared at a single patch of sky containing about 150,000 stars. It watched for planets passing in front of their stars, causing tiny periodic dips in brightness. Over 4 years, Kepler discovered thousands of planets. The results revolutionized our understanding of planetary systems. Planets aren't rare. They're the rule, not the exception. Most stars have planets. Some have many. The galaxy contains hundreds of billions of worlds, rocky planets, gas giants, ice worlds, planets with multiple suns, planets orbiting dead stars. And crucially, many of these planets orbit in their star's habitable zone, the region where temperatures allow liquid water to exist on a planet's surface. Kepler 452b orbits a sun-like star 1,500 light-years away. It's about 60% larger than Earth and receives roughly the same amount of light from its star that Earth receives from the Sun. It's been orbiting for 6 billion years longer than Earth has existed, giving plenty of time for life to develop if the conditions are right. We'll never visit Kepler 452b. At our current technology level, it would take tens of millions of years to reach it. We can't even determine with certainty whether it has a rocky surface or what its atmosphere contains. But we know it's there, a cousin Earth orbiting a sun-like star, possibly harboring oceans and continents and weather, and it's just one among thousands of potentially habitable worlds we've found. But finding planets in habitable zones isn't the same as finding life. Life requires more than liquid water and the right temperature. It needs the right chemistry, the right energy sources, the right environmental stability, and we still don't fully understand how life begins. On Earth, life appeared remarkably quickly. Our planet formed 4.5 billion years ago. It was initially molten, then bombarded by asteroids and comets during the late heavy bombardment that ended about 3.8 billion years ago. Within a few 100 million years after conditions stabilized, perhaps even sooner, life appeared. This quick emergence suggests life might form easily when conditions are right. Or it might suggest we got incredibly lucky. With a sample size of one planet with life, we can't tell the difference between probable and miraculous. But here's what we do know. Life doesn't need pleasant conditions. It just needs chemistry and energy. Earth's deep-sea hydrothermal vents host thriving ecosystems in complete darkness, where superheated water rich in chemicals provides the energy for life. Bacteria live in Antarctic ice. Microbes thrive in acidic hot springs. Life colonizes the most extreme environments Earth offers. This resilience has transformed our thinking about where life might exist in our solar system. Mars once had rivers and lakes, possibly oceans. Ancient shorelines are still visible in satellite images. Minerals that only form in liquid water lie scattered across its surface. But Mars lost most of its atmosphere billions of years ago, and its surface water evaporated or froze. Today, Mars is a frozen desert with an atmosphere too thin to breathe. Yet liquid water might still exist below the surface. Mars has ice caps at both poles. Ground-penetrating radar reveals what appears to be a lake of liquid water beneath the southern ice cap, kept liquid by salt and pressure. If life ever arose on Mars, it might persist in these subsurface refuges, protected from the harsh surface conditions. Europa, one of Jupiter's large moons, presents an even more intriguing possibility. Its surface is covered by a layer of water ice, but beneath that ice lies an ocean, a global ocean of liquid water that might contain twice as much water as all of Earth's oceans combined. How can water remain liquid on a moon so far from the Sun, where temperatures drop to minus 160 degrees Celsius? The answer is tidal heating. Jupiter's immense gravity flexes Europa as it orbits, like squeezing a rubber ball. This constant flexing generates heat through friction, keeping the subsurface ocean liquid. Images from spacecraft show Europa's surface is geologically young, with very few impact craters. The ice is constantly cracking, shifting, renewing itself. In some regions, scientists observe what appear to be plumes of water vapor erupting from beneath the ice geysers, shooting ocean water into space. If Europa's ocean has hydrothermal vents like Earth's deep seas, it might provide the chemistry and energy needed for life. Simple organisms could thrive in the darkness below the ice, feeding on chemical energy from the vents, never seeing sunlight, perhaps never even aware that a universe exists beyond their world of ice and water. Enceladus, a small moon of Saturn, presents similar possibilities. Despite being only 500 kilometers across, Enceladus has an active subsurface ocean. Geysers in its south polar region shoot water hundreds of kilometers into space. The Cassini spacecraft flew through these plumes and detected organic molecules, carbon-based compounds that are the building blocks of life as we know it. This doesn't mean life exists on Enceladus. It means the chemistry is there. The ingredients are present. Whether they've assembled into living systems remains unknown. Then there's Venus, Earth's hellish twin. Venus is nearly Earth's size and mass. It orbits closer to the Sun, but not dramatically so. Under different circumstances, Venus might have been Earth's sister, a warm, ocean-covered world where life could flourish. Instead, Venus experienced a runaway greenhouse effect. Its atmosphere, 90 times denser than Earth's, and composed almost entirely of carbon dioxide, traps heat so effectively that surface temperatures reach 470 degrees Celsius, hot enough to melt lead. The atmospheric pressure at the surface equals the pressure half a mile underwater on Earth. It rains sulfuric acid. The surface of Venus is as close to hell as our solar system offers. Nothing could survive there. But about 50 kilometers up, in Venus's upper atmosphere, conditions are surprisingly benign. The temperature drops to room temperature. The pressure equals Earth's surface pressure. You could float at this altitude in a balloon, and if you could somehow breathe the carbon dioxide and sulfuric acid droplets, you'd find the conditions almost pleasant. In 2020, scientists analyzing old Venus data and new observations announced they'd detected phosphine gas in Venus's clouds. On Earth, phosphine is produced primarily by anaerobic bacteria, organisms that don't need oxygen. There are some non-biological ways to produce phosphine, but none that seem likely on Venus. The announcement sparked intense debate. Some, Researchers suggested measurement errors or data processing problems. Others proposed exotic chemistry that might produce phosphine without life. Still others calculated that if bacteria were producing the phosphine, Venus's clouds would need about 1 million bacterial cells per cubic centimeter, less dense than Earth's atmosphere near ground level, but still enough to constitute a floating biosphere. The debate continues. Follow-up observations have been inconclusive, but the mere possibility that life might float in Venus's clouds, surviving by absorbing sunlight and metabolizing atmospheric chemicals, has transformed Venus from a cautionary tale about greenhouse effects into a potential habitat for aerial microbes. Meanwhile, the search for signals from technological civilizations continues. SETI, the search for extraterrestrial intelligence, uses radio telescopes to scan millions of stars, listening for signals that couldn't be natural. A deliberate transmission from an alien civilization would stand out from cosmic background noise like a lighthouse beam in fog. In 2019, astronomers detected an interesting signal from the direction of Proxima Centauri, our nearest stellar neighbor at just 4.2 light-years away. The signal, designated BLC-1, appeared at a narrow frequency and seemed to drift in a way consistent with coming from a planet orbiting the star. For months, the signal remained intriguing. Then researchers traced it to human-made interference, possibly from a satellite or ground-based transmitter whose signal had leaked into the telescope's data. BLC-1 joined a long list of false alarms. The most famous false alarm came in 1977. Astronomer Jerry Amon was reviewing data from the Big Ear radio telescope when he noticed a strong narrowband signal. It was so striking, so apparently artificial, that he circled it on the printout and wrote, "Wow," in the margin. The wow signal lasted 72 seconds, exactly as long as the telescope's observation window would allow for a cosmic source. It came from the direction of Sagittarius. It never repeated. Despite numerous follow-up observations, that patch of sky has remained silent. Was it aliens? Probably not. The signal likely came from a comet, or some other natural phenomenon we don't fully understand, but it remains unexplained, a reminder that the universe can surprise us in ways we haven't anticipated. The truth is, we're only beginning to search in earnest. We've examined perhaps 1 million stars with decent sensitivity. There are 400 billion stars in our galaxy. We've searched a tiny fraction of a percent of possible locations. Moreover, we're making assumptions about what alien signals would look like. We assume they'd use radio waves, because that's what we use. We assume they'd broadcast omnidirectionally, because that's what we'd do if we were trying to contact others. We assume they'd use a narrow frequency band, because that's what would stand out as artificial. But a civilization 1,000 years more advanced than us might use technologies we can't even imagine. They might have moved beyond radio communication centuries ago. They might use neutrinos or gravitational waves or something we haven't discovered yet. Looking for alien radio signals might be like someone in the telegraph era trying to detect cell phone signals. The technology exists, but it's invisible to outdated detection methods. This brings us back to the Fermi paradox. The great silence. Maybe we're alone. Maybe life is common but intelligence is rare. Maybe intelligence is common but technological civilizations destroy themselves before they can colonize the galaxy. A grim possibility given humanity's own near misses with nuclear annihilation. Maybe civilizations develop technologies that make interstellar travel and communication unnecessary. Maybe they upload themselves into virtual realities, living out their existence in simulated worlds more interesting than the physical universe. Maybe we're early. The universe is 13.8 billion years old, but it will continue for trillions of years. Maybe we're among the first intelligent civilizations to arise, and the galaxy will teem with life billions of years from now. Or maybe they're already here, but we don't recognize them. Maybe civilizations advanced enough to cross interstellar distances are so different from us that their presence is invisible to our primitive instruments and limited comprehension. The possibilities are endless, and the uncertainty is frustrating. But here's what we know with certainty. We live in a universe containing hundreds of billions of galaxies, each containing hundreds of billions of stars, most of which have planets. The raw materials for life, water, organic molecules, energy sources are common throughout the cosmos. The universe is vast enough and old enough that life should be common. Intelligence should exist somewhere besides Earth. And yet, when we listen, we hear only silence. This silence is either the universe's greatest tragedy or its greatest mystery. Perhaps both. But while we search the cosmos for company, there's another mystery much closer to home. It's a mystery about the very nature of time, how it flows, why it flows in one direction, and whether the past, present, and future all exist simultaneously in ways our consciousness can't perceive. Time's labyrinth awaits, and it's stranger than anything we've encountered so far. What is time? It seems like a simple question. Time is what clocks measure. It's the dimension in which events happen sequentially. It flows from past through present into future. Everyone knows what time is, except physicists. Physicists struggle with time in ways that would seem absurd if the mathematics and experiments didn't repeatedly confirm how strange time really is. Let's start with the most counterintuitive fact. Time began. 13.8 billion years ago, time itself came into existence along with space, matter, and energy. Asking what happened before the Big Bang is like asking what's north of the North Pole. The question contains a logical error. Before is a temporal concept that requires time to exist. Without time, there is no before. This isn't just philosophical wordplay. General relativity describes space-time as a unified four-dimensional structure. The Big Bang marks the boundary of this structure. Time and space emerge together from that initial singularity. There is no time before time began, no space outside space, no moment when the universe didn't exist and then suddenly did. Your intuition rebels against this. Mine does too. Our brains evolved to navigate a world where time flows steadily, where cause precedes effect, where past and future are fundamentally different. The universe's actual structure is far stranger than our intuitions suggest. Albert Einstein revealed just how strange in 1905 with his special theory of relativity. Newton thought time was absolute, that it flowed at the same rate everywhere in the universe, like a cosmic metronome ticking away the same seconds for everyone. Einstein discovered this was wrong. Time is relative. It flows at different rates depending on how fast you're moving. Here's what's really happening. Time and space are connected. When you move through space, you're also moving through time, but in a way that keeps the total speed through space-time constant. The faster you move through space, the slower you move through time relative to someone standing still. This isn't a small effect at everyday speeds. At highway speeds, time dilation is unmeasurable, but approach the speed of light and time does something extraordinary. Imagine twins, one stays on Earth, the other boards a spacecraft and travels to Alpha Centauri, 4.3 light-years away, at 99.9%. The speed of light. The journey takes about 4.3 years as measured from Earth, but inside the spacecraft, only about 2 months pass. The traveling twin experiences 2 months while the Earth-bound twin ages 4 years. The spacecraft turns around and comes home at the same speed. Another 4 years pass on Earth, another 2 months in the ship. When the twins reunite, the traveler has aged about 4 months while the Earth-bound twin has aged 8 years. This isn't science fiction, it's verified physics. Particles called muons, created by cosmic rays in the upper atmosphere, decay so quickly they shouldn't reach the ground except they're moving near light speed, and time dilation extends their lifespans long enough for them to complete the journey. GPS satellites experience time dilation every day. They orbit Earth at speeds of about 14,000 kilometers per hour, making their clocks run slightly slower than clocks on the ground. But they're also higher in Earth's gravitational field, where time runs slightly faster. The net effect: satellite clocks gain about 38 microseconds per day compared to ground clocks. GPS systems must correct for this, or navigation errors would accumulate by several kilometers per day. Time literally runs at different rates at different speeds and different gravitational strengths. This brings us to Einstein's even more mind-bending discovery: general relativity. Gravity isn't a force pulling objects together. Gravity is the curvature of space-time itself. Massive objects bend space-time like a bowling ball placed on a trampoline. Other objects follow the curved paths through this warped space-time, which we perceive as gravitational attraction. But curving space-time doesn't just affect space, it affects time too. The stronger the gravity, the slower time flows. Near a black hole, this effect becomes extreme. Sagittarius A star. Sagittarius asterisk. If you're reading, the astronomical notation is the supermassive black hole at the center of our galaxy. It contains 4 million times the Sun's mass compressed into a region smaller than Earth's orbit. Its gravity warps space-time so severely that time itself nearly stops at the event horizon. If you could watch someone fall toward this black hole while you stayed safely far away, you'd see them slow down as they approached the event horizon. Their movements would become sluggish. Their clock would tick slower and slower. From your perspective, they would take forever to reach the event horizon, asymptotically approaching but never quite crossing it, frozen in time at the boundary. But from the falling person's perspective, nothing unusual happens. They cross the event horizon in a finite time by their clock. Time flows normally for them. They don't feel time slowing down because everything slows down together. Their thoughts, their heartbeat, the light reaching their eyes. Once they cross the event horizon, no possible trajectory leads back out. All paths through space-time point toward the singularity at the black hole's center. Trying to escape a black hole is like trying to travel backward in time, mathematically impossible, forbidden by the structure of space-time itself. At the singularity, Einstein's equations break down. They predict infinite density, infinite curvature, infinite tidal forces. These infinities signal that we've reached the limits of general relativity. Something deeper, perhaps quantum gravity, must describe what happens at the singularity. But we don't have a theory of quantum gravity yet. What we do have is Stephen Hawking's discovery that black holes aren't completely black. Quantum mechanics describes empty space as seething with virtual particles, particle-antiparticle pairs that pop into existence and annihilate so quickly they can't be directly observed. Usually, these virtual pairs appear and disappear without consequence. But near a black hole's event horizon, something strange can happen. If a virtual pair appears right at the event horizon, one particle might fall into the black hole while the other escapes. From the outside perspective, the black hole has emitted a particle. Over immense timescales, this Hawking radiation causes black holes to evaporate. The smaller the black hole, the faster it evaporates. A black hole with the mass of our Sun would take 10 to the 67 years to evaporate, vastly longer than the current age of the universe. A supermassive black hole like Sagittarius A star would take 10 to the 100 years. These numbers are so large they're essentially meaningless. The universe will have ended in every conventional sense long before the black holes evaporate. But evaporate they will. And when they do, what happens to the information that fell into them? The quantum states of all the particles that crossed the event horizon, where does that information go? This information paradox remains unsolved. Some physicists think the information is preserved in the Hawking radiation, encoded in subtle correlations we can't yet measure. Others think information is truly destroyed, which would violate quantum mechanics. Still, others think the information is somehow stored on the event horizon itself, in a two-dimensional holographic encoding of everything that fell in. These questions push physics to its limits, where quantum mechanics and general relativity collide, and neither theory fully describes what happens. They also raise a deeper question: is time fundamental, or is it emergent? Some physicists argue that time, as we experience it, emerges from more fundamental timeless physics. In this view, the universe's quantum state is fundamentally static. It exists as a complete, timeless mathematical structure. The flow of time, the sense that the present moment is special, arises from how consciousness navigates through this static structure. This brings us to one of time's deepest mysteries, the arrow of time. Physics equations are almost entirely time-symmetric. If you film a collision between billiard balls and play the footage backward, the backward version obeys the same physical laws. The equations describing electromagnetism, gravity, even quantum mechanics work equally well forward and backward in time. Yet time clearly has a direction. You remember the past but not the future. Coffee cools but never spontaneously heats. Eggs scramble easily but never unscramble. Stars burn out. Living things age and die. The universe itself flows from order toward disorder, from low entropy toward high entropy. This is the second law of thermodynamics. In any closed system, entropy, roughly speaking, disorder increases over time. It's the only fundamental law of physics that distinguishes past from future. But why? The answer seems to be that the universe began in an extraordinarily low entropy state. The Big Bang was incredibly smooth, uniform, organized. As the universe evolved, gravity created structure, stars, galaxies, planets, and this structure creation actually increased entropy overall, even though local regions became more ordered. Here's what's really happening. Entropy increase isn't about things getting messier. It's about systems exploring more possible states. There are many ways for cream to be mixed into coffee, but only one way for them to be completely separated. Once they mix, the random motion of molecules almost never unmixes them, not because mixing is physically impossible, but because the number of mixed states vastly outnumber the unmixed state. Time's arrow emerges from probability. The future is the direction in which entropy increases because high-entropy states are statistically more likely than low-entropy states. The universe started in an improbably low-entropy state for reasons we don't understand, and it's been sliding toward higher entropy, toward heat death ever since. But some physicists question whether time flows at all. The block universe theory, also called eternalism, proposes that past, present, and future all exist simultaneously. Time is just another dimension, like the three spatial dimensions. The difference is that consciousness can only perceive one moment at a time, moving through time like reading words on a page. In this view, your birth, your death, and this moment all exist equally. They're all out there, in the four-dimensional space-time structure. The passage of time is an illusion created by consciousness, sampling these moments sequentially. This seems bizarre, but it's consistent with relativity. Einstein himself wrote, "The distinction between past, present, and future is only a stubbornly persistent illusion." In relativity, there's no universal now that extends across space. Events that are simultaneous for one observer happen at different times for another observer moving at a different speed. If there's no universal present moment, if simultaneity is relative, then all moments must be equally real. The past hasn't ceased to exist. The future isn't yet to come. Everything exists in the eternal now of the block universe, with consciousness creating the illusion of flow as it moves through this timeless structure. Quantum mechanics adds another strange twist. In the quantum realm, particles exist in superposition, multiple states simultaneously until observed. Schrödinger's famous cat is both alive and dead until someone opens the box and looks. The act of observation appears to collapse the superposition into a definite state. This has led some physicists to propose that consciousness plays a fundamental role in creating time's flow. Perhaps the now is defined by conscious observation collapsing quantum superpositions. Before observation, the future exists as a superposition of possibilities. Observation collapses these possibilities into a single actuality, creating the past. This suggests consciousness might be more Rebeccan word, fundamental than we thought, not an accident of biology, but a necessary feature of reality itself, the mechanism by which the universe actualizes one history from infinite quantum possibilities. Roger Penrose goes further, proposing that consciousness requires quantum processes. He suggests that microtubules in brain neurons maintain quantum coherence long enough for quantum computations to occur. These quantum processes, he argues, are what give rise to the strange, subjective, unified experience of consciousness. If Penrose is right, then consciousness is literally connected to quantum mechanics, to the deepest level of physical reality. Your awareness of the present moment might be a quantum phenomenon, inseparable from the universe's fundamental structure. Time also raises paradoxes about causality and free will. If the block universe is real, if all moments exist simultaneously, then the future is already determined. Your choices tomorrow already exist in the timescape. Free will becomes an illusion. You feel like you're making choices, but those choices were always going to happen because they already exist in the eternal structure of space-time. But quantum mechanics suggests true randomness exists. When a radioactive atom decays, there's no hidden mechanism determining the exact moment of decay. It's genuinely random, unpredictable, even in principle. If randomness is fundamental, then the future isn't entirely determined. The block universe would contain branching possibilities rather than a single fixed timeline. This connects to the many worlds interpretation of quantum mechanics, which we'll explore in more depth soon. But the key insight is that time might not be a single line from past to future. It might be a branching tree, with every quantum measurement creating new branches, new timelines, new futures. You might exist in countless timelines simultaneously, making different choices, experiencing different outcomes, all equally real in different branches of the quantum wave function. Time also appears to be quantized at the smallest scales. The Planck time, about 10 to the negative 44 seconds, represents the shortest meaningful interval. Below this scale, the concepts of space and time as smooth, continuous dimensions break down. Space-time itself becomes grainy, foamy, fundamentally quantum. This suggests time isn't infinitely divisible. You can't subdivide time intervals forever. Eventually you reach a fundamental tick, a smallest possible moment. Time becomes less like a flowing river and more like a film, discrete frames played fast enough to create the illusion of smooth motion. All of this points to a disturbing conclusion. We don't understand time. It's the most familiar aspect of existence. You experience it continuously, moment by moment, yet it remains profoundly mysterious at every level of analysis. Does time flow, or do we flow through time? Is the present moment special, or is it just one frame in an eternal block? Does consciousness create time's arrow, or is consciousness just a pattern of information flowing downstream in time? Is time fundamental, or does it emerge from timeless quantum mechanics? These aren't just philosophical questions. They're physics questions without definitive answers. Every approach to understanding time, from relativity to quantum mechanics to thermodynamics, reveals different aspects of its nature, but no unified picture emerges. What we do know is that time is stranger than you think. It began. It dilates, it curves, it might not flow, it might not be fundamental, and it's intimately connected to consciousness, to quantum mechanics, to the deepest mysteries of existence. Time is a labyrinth, and we've only explored a few of its corridors. But there's an even more bewildering possibility waiting in another wing of this labyrinth, the possibility that our universe isn't the only one, that every quantum event spawns new universes, that reality branches infinitely, creating a multiverse so vast that an exact copy of you exists impossibly far away, living a life nearly identical to yours. This is where physics meets infinity, where mathematics suggests possibilities so extreme they challenge our very concept of what it means for something to be real. The multiverse awaits, and it's infinite in ways you haven't imagined. Right now, as you listen to these words, countless versions of you exist in parallel universes. In one universe, you chose differently 5 minutes ago. In another, Earth never formed. In yet another, the fundamental constants of physics are different, creating a reality so alien it defies imagination. This isn't science fiction. It's a serious consequence of several different areas of physics, each pointing toward the same unsettling conclusion. Our universe might be just one of infinitely many. Let's start with the most direct version, the many worlds interpretation of quantum mechanics. In 1957, a graduate student named Hugh Everett proposed something radical. The standard interpretation of quantum mechanics said that particles exist in superposition, multiple states simultaneously until observed, at which point the wave function collapses into a single definite state. But this collapse seemed arbitrary, adding a special rule just to account for observation. Everett asked, what if the wave function never collapses? What if all possible outcomes actually happen? Here's how it works. Consider a quantum event with two possible outcomes, a radioactive atom that might decay or might not. In the standard interpretation, observation forces the atom to choose one outcome. In Everett's interpretation, the universe splits into two branches. In one branch, the atom decayed. In the other, it didn't. Both outcomes are real, occurring in parallel universes. Every quantum measurement creates branches. Every quantum event with multiple possible outcomes spawns multiple realities, each containing a different outcome. The branching happens constantly, everywhere, at every scale where quantum effects matter. The observable universe contains about 10 to the 80th atoms. Each atom undergoes countless quantum events, every second electrons changing energy levels, particles colliding, quantum fluctuations occurring. If each event with, say, two possible outcomes creates two universes, then the number of parallel universes grows exponentially. After just 1 second, there might be 10 to the 10 to the 80th parallel universes, a number so vast that writing it out would require more digits than there are atoms in our universe. And that's being conservative. The actual branching rate could be vastly higher. In this interpretation, you exist in countless variations across the multiverse. In some universes, you made different choices. In others, random quantum events in your brain produce different thoughts. In still others, quantum fluctuations billions of years ago created different initial conditions for Earth, and you never existed at all. Here's what's really happening. When you make a decision, say, whether to turn left or right, quantum fluctuations in your neurons might influence which way you choose. If many worlds is correct, both choices happen. The universe branches, and both versions of you are real, each unaware of the other, each experiencing their choice as the only outcome. This sounds extravagant. It multiplies reality beyond any reasonable necessity. But many worlds has advantages. It's mathematically simpler than standard quantum mechanics because it doesn't need the arbitrary collapse rule. It treats observers as ordinary quantum systems, subject to the same laws as everything else. And it might be testable. Some physicists are designing experiments to detect subtle interference effects that would only appear if parallel branches exist. But quantum many worlds is just the beginning. Cosmic. Inflation suggests something even more extreme. Remember inflation, the exponential expansion of space in the universe's first fraction of a second? The theory explains many features of our universe, from its flatness to the uniformity of the cosmic microwave background. But inflation creates a problem. If it can start, why would it stop? In eternal inflation theory, once inflation begins in any region of space, it continues forever in most of space. Quantum fluctuations create bubbles where inflation stops and a universe like ours forms. But outside these bubbles, inflation continues, and more bubbles form. The process never ends. Each bubble becomes its own universe, causally disconnected from all others. Light from other bubbles can never reach us because the inflating space between us expands faster than light can cross it. Each bubble universe has its own Big Bang, its own laws of physics possibly, its own history. The bubbles keep forming, forever, creating an infinite number of universe bubbles floating in an eternally inflating sea. Our observable universe is one bubble in an infinite foam of universes. This isn't speculation piled on speculation. It's a natural consequence of inflation theory, which explains observed features of our universe better than any alternative. If inflation happened once, the mathematics suggests it happens eternally. The multiverse isn't an add-on to the theory, it's an unavoidable prediction. String theory takes this even further. String theory proposes that fundamental particles aren't point-like objects but tiny vibrating strings. Different vibration modes create different particles. An electron is one, a vibration pattern, a quark is another, a photon is yet another. The theory elegantly unifies all fundamental forces and might be the long-sought theory of everything. But string theory requires more than our familiar 3 dimensions of space and 1 of time. The mathematics only works in 11 dimensions. 6 or 7 of these extra dimensions are curled up so small we never notice them. But they exist, and their geometry determines the laws of physics we observe. Here's where it gets wild. There are about 10 to the 500 different ways these extra dimensions can be configured. Each configuration produces different physical laws, different particle masses, different force strengths, different values for fundamental constants. This is called the string theory landscape. Each of the 10 to the 500 configurations might correspond to a real universe somewhere in the eternally inflating multiverse. In most of these universes, the laws of physics are unsuitable for life. Stars don't form, or atoms don't hold together, or chemistry is impossible. We exist in one of the rare universes where the physical constants permit complexity, structure, and ultimately life. Not because we're special, but because in universes where life can't exist, there's no one to observe that fact. This is the anthropic principle, and it's deeply controversial. Some physicists embrace it. The universe appears fine-tuned for life because we're selecting from a vast multiverse containing every possible value of physical constants. We necessarily find ourselves in a rare universe suitable for observers. Other physicists hate it. It seems to abandon the search for deeper explanations. Instead of asking, why do physical constants have these specific values? The anthropic principle answers, because if they didn't, we wouldn't be here to ask. It feels like giving up, like replacing physics with tautology. But consider the evidence for fine-tuning. Change the strength of gravity by 1 part in 10 to the 60th, and stars can't form, either they burn out instantly or never ignite. Change the strong nuclear force by a few %, and atomic nuclei can't hold together. Change the cosmological constant by any significant amount, and either the universe collapses immediately or expands, so fast that galaxies never form. The parameters seem impossibly well calibrated. Either we're extraordinarily lucky winning a cosmic lottery with odds of 1 in 10 to the 100 or worse, or there are countless universes with different parameters, and we necessarily inhabit one where the parameters permit our existence. The anthropic principle offers an explanation, but it's an explanation that might be forever untestable. We can't observe other universes. We can't measure their physical constants or verify their existence. The multiverse might be real, but permanently beyond empirical investigation. This troubles many physicists. Science requires testable predictions. If a theory predicts an infinite multiverse we can never observe, is it still science? Yet the multiverse keeps appearing in different contexts, suggested by independent lines of reasoning. That's unusual. When multiple areas of physics independently point toward the same conclusion, it often means something real is there. Max Tegmark organized these ideas into a hierarchy of multiverses, each more radical than the last. Level 1. The infinite universe. If space is infinite and matter is distributed more or less randomly, then everything that can happen does happen somewhere. Given infinite space, there must be regions identical to our observable universe. Exact copies of you exist, living identical lives. In fact, the nearest exact copy of you exists about 10 to the 10 to the 29 meters away. That distance is incomprehensible. To write it out, you'd need more atoms than exist in the observable universe. You could never reach your copy, even traveling at light speed forever. But if space is truly infinite and the universe is roughly uniform, these copies must exist. Level 2. The eternally inflating multiverse we already discussed. Different bubble universes with potentially different physical constants, created by eternal inflation. These universes are causally disconnected. We can never interact with them or even observe them. Level 3. The quantum many-worlds multiverse. Every quantum event creates branches, and all branches are real. This multiverse exists alongside ours, in a different sense, not in distant space, but in superposition, in a higher dimensional quantum state space. Level 4. The mathematical universe hypothesis. This is Tegmark's most radical proposal. He suggests that every mathematically consistent structure exists physically. Our universe is one mathematical structure among infinitely many. Other universes might have different numbers of dimensions, different mathematical laws governing their evolution, even different logics where 2 plus 2 doesn't equal 4. In this view, mathematics isn't a language we invented to describe reality. Mathematics is reality. Every equation that could be written, every mathematical structure that could exist, does exist as a physical universe somewhere. We happen to inhabit a universe whose mathematical structure permits complex information processing and consciousness. This sounds insane, but Tegmark argues it's the simplest explanation for why mathematics describes our universe so perfectly. The universe isn't following mathematical laws, it is a mathematical structure, and we're patterns of information within that structure. Each level of multiverse raises profound questions about probability, existence, and reality itself. If infinitely many versions of you exist, making every possible choice, does free will mean anything? If every outcome happens somewhere, are your choices significant? If most universes are lifeless or hostile, and we necessarily exist in a rare exception, does that make our universe less remarkable or more? Are we special because we exist in a universe that permits life? Or are we utterly unremarkable because somewhere in the multiverse, every possible configuration exists? If mathematical structures are physically real, does that mean fictional universes exist somewhere? Does Middle-earth exist as a real place in some universe whose mathematical structure permits its geography and physics? What about universes where consciousness works differently, where time flows backward, where nothing remotely resembling our physics applies? These questions push beyond science into philosophy, but they're motivated by physics, by mathematical structures that seem to describe our universe accurately and then predict consequences we can't yet verify. Some physicists propose tests. If our universe is one bubble among many, Collisions with other bubbles might leave circular patterns in the cosmic microwave background, bruises in the sky marking ancient impacts. Researchers have looked. So far, nothing. But absence of evidence isn't evidence of absence when you're trying to detect something as subtle as a universe collision billions of years ago. Quantum many-worlds might be testable through quantum computer experiments that detect interference between branches. If successful, such experiments would provide evidence that parallel outcomes remain real rather than collapsing into a single outcome. But these tests face enormous practical challenges. The universe doesn't make it easy to prove or disprove its own multiplicity. Meanwhile, the fine-tuning problem remains. Why is our universe so precisely calibrated for complexity? The multiverse offers an answer, but it's an answer that abandons the quest for a deeper why. It replaces explanation with anthropic selection. Some physicists still hope for a theory that predicts the physical constants from first principles, showing that the universe must be this way, that no other configuration is mathematically consistent. If such a theory exists, it would eliminate the need for anthropic reasoning and restore a sense of cosmic uniqueness to our universe. But no such theory has emerged. Instead, we have string theory's landscape of 10 to the 500 possibilities, most of which probably exist as real universes somewhere in the eternally inflating multiverse. Here's what's really happening. Physics has pushed beyond the observable, and possibly beyond the testable. We've entered a realm where mathematics and theory point toward realities we may never confirm through experiment. The multiverse might be real, but proving it requires evidence we might never obtain. This is unsettling for a field built on empirical verification, yet the mathematical structures that produce the multiverse, quantum mechanics, inflation, string theory, are the same structures that make accurate predictions about phenomena we can test. We can't pick and choose which predictions to take seriously just because some feel more comfortable than others. If the math says parallel universes exist, and that math successfully describes everything else about quantum mechanics, on what grounds do we dismiss the parallel universes? If inflation explains the cosmic microwave background's uniformity, and inflation naturally produces eternal inflation and bubble universes, can we accept one prediction while rejecting the other? These are questions without clear answers, marking the current frontier where physics confronts the limits of human knowledge and possibly of human knowability. But while we grapple with the existence of parallel universes we can never visit, there's a more immediate question about the universe we do inhabit. What is our role here? Did the universe need consciousness to observe itself into existence? Is intelligence an inevitable product of cosmic evolution, or an improbable accident? And what happens when consciousness meets the universe's ultimate fate? The heat death that awaits trillions of years hence, when the last stars fade and even black holes evaporate. These final questions bring us to the deepest mystery: consciousness itself, its place in the cosmos, and whether mind might be more fundamental than matter. Whether, in some sense, the universe exists because consciousness exists to perceive it. That story, the convergence of cosmos and consciousness, is where our journey concludes. Look up at the night sky. Those stars, each one a nuclear furnace, each hosting possible worlds, won't last forever. Our sun will exhaust its hydrogen fuel in about 5 billion years. It will swell into a red giant, engulfing Mercury, Venus, possibly Earth. Then it will shed its outer layers, leaving behind a white dwarf, a stellar ember gradually cooling over trillions of years until it becomes a black dwarf, a dark cinder floating through space. Massive stars die more dramatically. They explode as supernovae, briefly outshining their entire galaxies, then collapse into neutron stars or black holes. But even these spectacular deaths are temporary phenomena. Eventually, even the most dramatic stellar remnants will fade or evaporate. In 100 trillion years, 100,000 billion years, the last conventional stars will flicker out. The universe will enter what's called the degenerate era, populated only by fading stellar remnants, white dwarfs, neutron stars, and black holes. The universe will be darker than you can imagine. No fusion fires will burn, no new stars will form. All the available hydrogen will be locked up in dead stars or dispersed too thinly to coalesce. Any civilizations surviving into this era will need to harvest energy from the rotational energy of black holes or the feeble heat of dead stars, eking out existence on the thermodynamic dregs of a dying cosmos. But the universe has much longer to go. Much, much longer. Over 10 to the 30 years, 1,000 billion years, even the most stable structures will decay. Protons, the fundamental building blocks of atomic nuclei, might be unstable at these timescales. If they decay, everything will eventually dissolve into lighter particles and radiation. The white dwarfs, neutron stars, even the planets will slowly evaporate particle by particle, their matter converting into energy and dispersing into space. By 10 to the 40 years, if protons decay, ordinary matter will be essentially gone. Only black holes will remain, and they're evaporating too. Stephen Hawking's discovery that black holes emit radiation means they have a temperature, and anything with a temperature radiates energy. A black hole with the sun's mass would take 10 to the 67 years to evaporate completely. Supermassive black holes, those containing billions of solar masses, will take 10 to the 100 years or more. These timescales are so vast they lose meaning. The current universe is less than 14 billion years old, 14 times 10 to the 9. We're talking about timescales 10 to the 90 years in the future. If the universe's current age were compressed into a single second, the black hole evaporation era wouldn't begin until the universe was already older than 1 billion years. By 10 to the 100 years, even the largest black holes will have evaporated through Hawking radiation. What remains? Elementary particles, photons, neutrinos, electrons, positrons, separated by distances that dwarf our current observable universe. The average distance between particles will be greater than the size of today's visible cosmos. The universe will have reached maximum entropy heat death. No temperature differences exist to drive processes. No energy concentration remains to power computation or life. The universe achieves thermodynamic equilibrium, unchanging and silent, persisting in this state, potentially, forever. This is the depressing projection of cosmic eschatology based on our current understanding of physics. The universe dies not in fire but in ice, in cold, dark, empty silence. But something extraordinary happened along the way, something the universe wasn't obligated to produce, but did anyway: consciousness. Somewhere between the quantum and classical worlds, between mere chemistry and subjective experience, matter organized itself into patterns capable of awareness. On Earth, about 4 billion years ago, self-replicating molecules emerged from chemistry. Over billions of years, evolution sculpted these molecules into organisms of increasing complexity. 540 million years ago, during the Cambrian explosion, complex body plans suddenly appeared. Eyes evolved, nervous systems became more sophisticated. Animals began modeling their environment, predicting the future, making decisions based on internal representations of reality. Eventually, one species, humans, developed consciousness so sophisticated it could contemplate the universe itself. We're made of atoms forged in dying stars, arranged by evolution into configurations capable of understanding how those atoms were forged. We're the universe's way of knowing itself. But what is consciousness? How does subjective experience arise from objective matter? This is the hard problem of consciousness, and it remains unsolved. We understand the neural correlates of consciousness, which brain regions activate when you're conscious, which patterns of electrical activity correspond to different experiences. But we don't understand why these physical processes create subjective experience. Why is there something it's like to be you? Why does the pattern of electrons firing in your brain create the sensation of seeing red, the feeling of joy, the experience of tasting chocolate? In principle, you could imagine a universe where all the same physical processes occur without any subjective experience. Philosophical zombies who behave identically to conscious beings, but with no inner life. Yet we know we're not zombies. We have inner experience. Why? Some philosophers think consciousness is fundamental, that it's a basic feature of reality, like mass or charge, not reducible to simpler components. Others think it's emergent, that it arises from sufficiently complex information processing without being fundamental. Roger Penrose proposes that consciousness requires quantum processes. He points to microtubules in neurons, tiny cellular structures that might maintain quantum coherence long enough for quantum computation. In this view, consciousness is literally quantum mechanical, arising from the collapse of quantum superpositions in the brain. Most neuroscientists are skeptical. The brain is warm, wet, and noisy, exactly the kind of environment where quantum coherence should be impossible to maintain. But Penrose argues that evolution might have found ways to protect quantum states, using them for computations that classical neurons alone couldn't perform. If consciousness is quantum mechanical, it connects directly to the deepest level of physical reality. Your thoughts, your sense of self, would be fundamentally quantum phenomena. And in a many-worlds interpretation, different outcomes of quantum processes in your brain would create different branches of consciousness, different versions of you experiencing different thoughts. Another approach views consciousness through the lens of information theory. Integrated information theory, developed by Giulio Tononi, proposes that consciousness is a measure of how much integrated information a system generates. The more a system's parts work together to create unified information that's more than the sum of its parts, the more conscious it is. By this measure, a human brain generates enormous amounts of integrated information at different regions, processing different aspects of experience, but unified into a single conscious perception. A simple system like a thermostat generates almost no integrated information, its components barely interact. It's not conscious, or conscious at such a minimal level it's meaningless to call it awareness. This theory predicts that any system generating sufficient integrated information would be conscious human brains, possibly animal brains, potentially even future artificial intelligence systems if they achieve the right kind of integration. It also suggests consciousness is a spectrum, not a binary. You're more conscious than a mouse, which is more conscious than an ant, which might be barely conscious at all. Consciousness admits degrees, from minimal awareness to rich, complex experience. But why does the universe produce consciousness at all? The standard story says it's an evolutionary accident. Consciousness helped our ancestors survive, modeling the environment, planning for the future, cooperating in social groups. It's a useful adaptation that happened to evolve on Earth, and presumably on other planets where similar selection pressures exist. Yet some physicists wonder if consciousness plays a deeper role. In quantum mechanics, observation appears to collapse superpositions. The double-slit experiment shows particles behaving like waves until measured, then collapsing into definite positions. Some interpretations suggest consciousness is necessary for this collapse, that awareness literally brings reality into existence. This is the participatory anthropic principle, proposed by John Wheeler. He suggested that observers are necessary to bring the universe into being, that consciousness and reality are mutually dependent. The universe creates observers, and observers actualize the universe through observation. This sounds mystical, but it's grounded in quantum mechanics' measurement problem. If observation collapses superpositions, and consciousness is necessary for observation, then consciousness plays a fundamental role in determining reality. Most physicists think this goes too far. Observation in quantum mechanics doesn't require conscious observers. Any interaction that records information counts as measurement. A particle interacting with a detector collapses. Superposition, whether anyone looks at the detector or not. But the fact that consciousness emerged at all remains remarkable. The universe spent 10 billion years after the Big Bang, producing the conditions for life-forming elements in stellar cores, creating planets, establishing stable environments. Then, another 4 billion years of evolution on Earth, before consciousness sophisticated enough to understand the universe emerged. It's as if the universe prepared a stage for 10 billion years, then spent 4 billion years evolving an audience capable of appreciating the show. And the show is spectacular galaxies wheeling through space, stars dying and being born, black holes devouring matter, quantum fluctuations creating virtual particles, space-time itself expanding and curving. We exist in perhaps the most interesting era of cosmic history. The universe is old enough to have created complex chemistry and life, but young enough that stars still burn, galaxies still shine, and the cosmic web is still visible. Billions of years from now, in the degenerate era, any consciousness that survives will look out on a dark, nearly empty universe with far less to observe. But could consciousness survive that long? Could intelligence persist billions, trillions, or even 10 to the 100 years into the future? Some theorists think it's possible. Freeman Dyson calculated that consciousness might survive indefinitely, even in an ever-expanding universe, by operating more and more slowly as available energy decreases. Think for a second, sleep for a century. Think for another second, sleep for a millennium. The total computational work accomplished could be infinite, even as the universe approaches heat death. Others propose that advanced civilizations might manipulate the structure of space-time itself, creating closed time-like curves that allow them to process infinite information in finite time as they approach a singularity, Frank Tipler's omega point. In this scenario, consciousness expands to encompass the entire universe in its final moments, achieving something like omniscience just before the end. These ideas are speculative, pushing far beyond established physics, but they represent attempts to answer a profound question. Does consciousness have a cosmic destiny, or is it a brief accident, flickering briefly in a universe that will ultimately extinguish all complexity? Perhaps the answer depends on what consciousness does with its time. Humanity has existed for about 300,000 years, civilization for 10,000, science for 400, technology for 200. We're infants in cosmic terms, barely beginning to understand the universe we inhabit. Yet we've already accomplished something remarkable. We've decoded the universe's history. We've traced reality back to the first second after the Big Bang. We've mapped the cosmic web. We've discovered that space itself is expanding, that time is relative, that quantum mechanics describes reality in ways that defy intuition. We've found thousands of exoplanets. We're searching for life beyond Earth. We're beginning to manipulate matter at the atomic level, to create artificial intelligence, to modify our own biology. We stand at a threshold. The next few centuries will determine whether consciousness on Earth survives its own ingenuity or destroys itself through climate change, nuclear war, engineered pandemics, or other existential risks. If we survive, the possibilities are extraordinary. We might spread beyond Earth, establishing settlements on Mars, Europa, exoplanets around other stars. We might merge with our technology, enhancing our intelligence, extending our lifespans, uploading our consciousness into substrates that don't require biological bodies. We might even find ways to outlive the stars, harvesting energy from black holes, moving computation to cold environments where quantum computers operate most efficiently, or discovering new physics that allows energy generation beyond chemistry and fusion. In the longest term, we might face the universe's end, whatever form that takes. If dark energy remains constant, the universe expands forever, growing cold and empty. If dark energy increases, we might face a big rip, where acceleration becomes so extreme that it tears apart galaxies, solar systems, planets, eventually atoms themselves. If dark energy somehow reverses, we might face a big crunch, with the universe collapsing back to a singularity. Some theories suggest this could lead to a big bounce, a new Big Bang, a new universe emerging from the old one's ashes. Could consciousness survive such transitions? Could we encode our existence in ways that persist through cosmic cataclysms? Could we create new universes ourselves, escaping to pocket realities of our own making? These questions border on science fiction, but they're grounded in real physics and real existential questions about consciousness's ultimate fate. What we know is this: consciousness is the universe's most remarkable achievement. In you, billions of years of cosmic evolution have produced a structure capable of understanding its own origins. You're made of atoms forged in stellar cores, arranged by evolution into a pattern that can contemplate stars, galaxies, and the very nature of existence. You are, quite literally, the universe made conscious. You're the cosmos looking back at itself, experiencing its own grandeur, marveling at the improbability of its own existence. This is either the most beautiful accident or the most profound destiny. Either consciousness is a brief spark in a universe that cares nothing for it, or it's the universe's purpose, the reason why anything exists at all. Ancient Mesopotamian priests looked up at the stars and saw gods. We look up and see nuclear fusion, gravitational lensing, red-shifted galaxies racing away from us as space itself expands. We understand more than we ever have, yet mysteries proliferate faster than answers. What is dark matter? What is dark energy? How did life begin? What is consciousness? Are we alone? Do multiple universes exist? What happens at the singularity of a black hole? How does quantum mechanics merge with gravity? What came before the Big Bang, if anything? Each answer raises new questions. Each mystery solved reveals deeper mysteries. The conversation that began 5,000 years ago in Mesopotamia continues, growing richer and stranger with each generation. You're part of that conversation. Your consciousness, your awareness of these words, your contemplation of cosmic questions represents the universe trying to understand itself. Whether that understanding has meaning beyond itself, whether it serves some cosmic purpose, or is simply a beautiful accident, remains unknown. But it is beautiful. The fact that matter can organize itself into patterns capable of experiencing wonder, of asking questions about existence, of contemplating infinity, this alone is extraordinary. Whatever the universe's ultimate fate, whatever lies beyond our cosmic horizon, whatever deeper reality might underlie quantum mechanics and space-time itself, we exist. We're here. We're conscious. We're the universe made manifest, experiencing its own mystery. That's worth something, perhaps everything. The stars that ancient priests watched are still there, though many have died and been replaced by new ones. The questions they asked are still being asked, though our answers are more sophisticated. The wonder they felt is still felt by every person who looks up at the night sky and asks, "What is all this? Why does anything exist? What does it mean that we're here to ask?" These questions may never have final answers. The universe might be more strange than we can suppose, containing layers of reality we haven't imagined, operating on principles we haven't discovered. But the search itself, the patient, incremental, occasionally revolutionary process of understanding reality more deeply, is humanity's greatest achievement. It's what consciousness does when it survives long enough. It explores, it questions, it seeks to understand. You're part of that search. You're heir to 5,000 years of accumulated knowledge, standing on insights built by countless minds across countless generations. And you're passing the torch forward, whether you realize it or not, to future generations who will know more, see farther, understand deeper. The conversation with the cosmos continues. It began when the first human looked up and wondered. It continues as long as consciousness persists to ask questions and seek answers. Where it leads, no one knows. But the journey, the gradual unveiling of reality's deepest secrets, is its own reward. Welcome to the universe. You're made of it, you're part of it, and in a very real sense, you are it, the cosmos conscious of itself, experiencing its own magnificent mystery. The wonder is real. The universe is stranger than we imagined, and the conversation has only just begun.